Okay, in our second real multivariable calculus limit, we're going to do a limit that's actually more complicated, but I'm going to start it the exact same way. If I plug in 0 for x and 0 for y, I get 0 over 0. That's indeterminate. There's no algebra I can do that really simplifies that, so we're going to try to start taking paths. And this one's going to require, at least while we're doing it, a lot of paths to think about. If I take, for example, y equals x, what am I going to get? I'm going to get x squared. Let's see, that's x to the 7/3, I think. X to the 7/3 of y on top. On the bottom, I'm going to get x plus x cubed. And I want to take the limit. Instead of saying x gets close to 0, 0, I'm just going to say x gets close to 0. It means the same thing, which is great. I still get 0 over 0, so I want to do the Calc 1 thing, and I want to factor and cancel. I see that I can factor an x off the top and an x off the bottom and cancel. So doing that, what I'm going to get is x to the 4/3 on top, and the canceled after x on bottom, I get 1 plus x squared. And I now can plug in, and I get sort of an anticlimactic 0. All right, so at the moment, we took one path, and we got one answer 0. Let's pick a different path. Let's try what we did before and say y equals 2x. And that's our second path. If I try y equals 2x and taking the limit, what am I going to get on top? Let's see here. This is going to be 4x squared, so this is going to be 4x to the 7/3. On the bottom, I'm going to get x plus 8x cubed. Try to take a limit again. I'm not going to write down x, 2x is close to 0, 0, because if x gets close to 0, so does 2x. So we are doing, after all, now a one variable limit. I see as before, I can take an x off the top, an x off the bottom, and cancel. So I'm just going to write down what we get. I'm going to get the limit. I'm going to get x goes to 0. X off the top gives me 4x to the 4/3. On the bottom, I'm going to get 1 plus 8x squared. And just as we got before, I got 0 again. And by the way, what does that show? Nothing, right? There might be another path out there where you get to a different height. There's an infinite number of paths. And if I actually had to show the limit did exist this way, I would have to show at least that every path gave me the same answer. Meanwhile, I did y equals x, y equals 2x. What if I try to be a slightly more general, or a lot more general? And let's put a formula in for any line through the origin. So how about something like y equals mx? So we're still walking on this crazy surface, right? Whatever it's doing, but we're staying on a line as we're headed over to the origin. This does have the benefit of simplifying again the same way we did before. I have to be a little bit careful here. I'm going to get m squared. Let's see here. I think it's x to the 7/3 again. And this is going to be x. Y cubed. This is going to be m cubed x cubed. M cubed x cubed. We are taking the limit. Right? And I don't want to say that mx gets close to 0, 0, because if x gets close to 0, so does mx. So I still get our one variable limit, which is great. I can still cancel off an x the same way I did before. So I'm going to say limit. This is still x gets close to 0. I'm still going to get m squared. Write this out so we can read this once. M squared, x to the 4/3, On the bottom, it's going to be 1 plus m cubed x squared. Let's see here. Did I do that? Yes. No. Yes, I canceled. Yay. Okay, right. And now I can plug in, and I get 0. So if we walked over the line, y equals x, we got 0. If we walked along the line, y equals 2x, we get 0. If we walk along any possible line, remember we're walking on the surface over that line. This is the shadow of our path in the xy plane. We get 0. What does that show? Nothing. You really have to remember that we would actually have to show that every possible path would end up at height 0. Now, this is typical of this kind of thing, and this is what I want to do. I'm going to try a different kind of path, one that doesn't go straight. Now, what I really want to be able to do is do something so that I can combine this x and the y cubed. So what I'm actually going to do is choose the path x equals y cubed. That way, I can combine stuff on the bottom. Let's do the bottom first, right? This is going to be y cubed plus y cubed. That's 2y cubed. That's great. The y squared is just y squared. The cube root of x is just y. I guess I'll write this over here somewhere. I'm going to regret this later. So that just puts another y right here, like that. And I'm going to try and take the limit. Put this little box over here so it's... we want the limit. Not limit inf. We want the limit. As y goes to 0 because our variable is now y. And what did we decide the top was? That could be y times y squared. That's y cubed. Like that. The bottom was y cubed plus y cubed. That's 2y cubed. Like that. And we're back to Calc 1. This is the one variable limit. I can't plug in, but I now can cancel. I can cancel a y cubed off the top, a y cubed off the bottom, leaving a 1 on top. And what we get is not 0. What we get is 1/2. Now, why did I put a frowny face? That means the limit doesn't exist. Now, this is a crazy kind of surface, and you can see why making, I think, any kind of graph of this surface would really lead to problems. This says if we walk along the line, any possible line through the origin, we always end up at the height 0. But if we take some sort of crazy S-shaped path, we end up at a half, right? So let's first write a conclusion. Conclusion says the limit doesn't exist. Why? Because we could find 2 different paths to walk along the surface that end up at different heights. Now, how in the world did I decide to pick x equals y cubed? I just picked something so that the bottom, I could combine the 2 terms evenly. That seems to work with a lot of these. So if drawing lots of lines through the origins keeps giving us the same value, try to make a substitution and a path that makes the bottom 1 term. And you can see how I did that. The problem I'm having you doing the activity is very similar, but it's a bit easier and it's a bit more of a common example. I wanted to try a hard one first. Anyways, those are the examples that we're going to do for the limit doesn't exist.